Okay, so let's get started. Right, so let's first do a review of last time. So last week we covered the per unit system. So the per unit system basically is a way of working with different voltage power levels in the system, right? So last time we saw an example, let's say you have a generator, connect to a transformer, connect to a transmission line, connect to another transformer, then connect to a load. Then per unit basically is a way to abstract away the transformers that we have in the system. Okay, so by choosing the correct per unit system, we don't need to write the transformers anymore. We can pretend this becomes a simple circuit of a voltage, connect to some resistance, inductance, and the impedance as a load. Okay, so that's the goal of per unit system. And for almost all calculations that any software will do or that you will do will be done in per unit system. Okay, any of the data sheets we see, most things are given in per unit systems, right? This just makes it easier for us to work with this kind of problems. So as a reminder, when we're setting the per unit system, we're picking the power. So the power base unit, this is something we can pick freely. Okay, right? So if you have looked at the homework, you'll see that the homework will tell you to pick a power at some rating, right? Pick a base power at some value. So this is what we can pick freely. Okay, this is in some sense arbitrary. Then we need to pick the voltage. Right? So it's normally best to pick the voltage at the rated voltages. So we have a transformer, let's say that we have a transformer. On one side, it's so this is rated V1, V2. Then on this side, we'll pick V1. On this side, we'll pick V2 as a base for the voltage, right? So if we pick the power arbitrarily and pick voltage this way, then if we do all the conversions correctly, we can basically just have a complex circuit for analysis, right? So we have a complex circuit to work with and not to worry about transformers. Okay? So that's the whole point of the per unit system. Right, so you'll see a lot of this in this week's homework. You'll see quite a number of problems like this. And most of them come down to finding the right equation, right? So when do you multiply by n1 over n2 squared, this kind of thing, right? When do you divide, when do you multiply by the base power or by the base voltage, right? So operationally it comes down to remembering these equations. And so of course, if you use a software, then all this is handled within the code. But for us in this class, you still need to do the work, right? So it's best to do the work and remember the equations, okay, for this kind of problems. Any question about the material that we covered?
I have a question from the homework, Professor.
Yeah, go ahead.
In problem 4, I was wondering, like, if we can solve it without knowing the power factor.
Problem 4. Okay, so let me look at problem 4. So problem 4 tells you the power factor, right? That's unity power factor?
Yeah, I didn't understand, like, what does it mean?
Oh, unity power factor means power factor 1.
Okay.
So unity, yeah. So unity power factor means 1. 1.0
Cool.
power factor.
Thank you.
Yeah. Yeah, so any other questions about things like this?
Yeah, Professor.
Yeah, go ahead.
Can I also ask like problem 4?
Sure.
Is problem 4 a practical transformer?
So what do you think if you read the question?
I think it is a practical transformer.
It is, right? It has a series impedance of
So
1
does
plus
it mean
J2.
like the 1 plus J2? Is
Yeah.
it like the series transformer? Sorry, series impedance for pointing one. So we need to find like the Z2 point for it.
No, so this is already referred to the primary, right? So
So that's
this means you refer Z2 to the primary and you add it up to whatever the primary winding has, and together we have a series impedance of this.
oh, so that's it's already added up.
Yeah, so the question says it has a series impedance referred to the primary, means everything has been referred to the primary. Yes.
Oh, okay. Thank you.
Yeah. Yeah, any other questions? Yeah, so if you have questions, please ask. Please ask, right? So if you don't want to lose points on these sort of questions, right? You don't want to make the question more complicated than it is. Okay, so any questions you can ask here, ask during the break, email me or Trisha. So please do ask a question about homework. Okay. So right now, only in the office hour, at least in my office hour, 1 or 2 people show up. So that's fine if you don't have questions. But then at the end of the quarter, please don't say that there's not enough office hours for this class. So make use of them, right? So if you have questions to ask, right? So if you don't, that's fine. But don't think these are bad questions or wrong questions, right? So especially if you have a question about the homework, right? You don't want to end up spending an hour on a problem, figuring out that for this case, for example, there's no series impedance at the secondary, and somehow you made some very complicated assumption about what happens and made it harder than it needs to be. Okay? So that's in general for this kind of question. This calculation question is not trying to trick you, right? So you find something really tricky or you're missing a value, then you should ask, right? Ask us about what it means, okay? For the homework. All right. So today what we'll do is we'll finish the per unit system. Okay, we'll basically do some more examples, and we'll look at what happens for 3-phase power flow. And the 3-phase is exactly the same as single phase, except we multiply by √3. Okay, so that's what 3-phase always boils down to be. So we'll finish the per unit system for 3-phase transformers. Then we'll go to transmission lines. So that's we'll try. And this week we'll try to finish the transmission line. So we'll try to finish the transmission line part. So but if you again, as a reminder of the class, what we're doing is we're basically trying to get each piece of the power system so we can model it as a circuit. Then we're going to try to solve problems with this circuit, right? But together requires some math and requires some effort. Although by the time we get there, everything will seem very simple, right? So now it's all, for example, per unit is a way to get rid of transformers, right? So, but which is not necessarily something that is obvious if you don't know about it. So if you know about it, it seems obvious. We can do this. But if you don't know about it, it's a nice trick, right? So it's something good to know, okay, about this kind of engineering tricks. So let's continue with the per unit system. So let's do more and more example, look at the example 3.4 in the book. And I copy the circuits here. So this problem says the following. We're given this circuit, basically. This is the whole circuit we have. And our goal is to draw the impedance circuit, find the load current. So we'll draw the circuit, do some calculations in the circuit. Okay, and again, there's no shunt, right? So we're going to ignore shunt. So often we'll just ignore shunt. So let's say we have this, so we're given everything here in per unit, but the problem is they are not in the same base, right? So this is in a circuit diagram, but the problem is we have 3 voltage zones and they are not in the same base. Okay, so let's try to make sure that we can convert all this to the same consistent circuit, right? And then try to do analysis on this. Okay? So again, the first goal is to let's pick. So the goal is to let's pick a power unit. Okay, so let's pick a power base unit for the power. So here we're going to pick a base. Pick for power, we're going to pick SB to be 30 kVA. Okay, so again, for most problems, you'll be told which unit to pick, which value to pick. So here we'll pick 30 kVA as a power unit. Okay, and now we have basically different voltages, and we need to convert them to a consistent basis. Okay, right. Okay, so now we have so for each of the voltage basis we're given here, as we'll pick 240 for the first one, pick 480 for the second one, and pick 120 for the third one. Okay, we're going to pick all these. Okay, so now, yeah, any questions?
I have a question.
Yeah, go ahead.
So when you were choosing the base unit for the power, just like kind of simply, how did you come across 30 kilovolts? I know that we're not normally going to have to do it. I'm just curious.
Oh, so this from the, if you read from the textbook, and well, the textbook gives a little bit more information about the first transformer. So here we're going across a transformer, right? And this T1 is rated at 30 kVA, 240, 480. T2 is rated at 20 kVA, 460, 115. Both. So normally if we pick a power base, we either pick one of the rated power for the transformers, or we'll pick a value that's comparable to the maximum low power we have in this circuit.
I see, thank you.
So for this problem, we could have picked 20, right? We could, pick 30, we could pick 50 for a round number. Normally it's those kind of ballpark choices we can pick.
Okay, makes sense.
Yeah. Yeah, so so normally the units goes by 50, 100, 200, 1,000, things like that. So it's a round number. Right? So here we'll pick 30. That's a rough number we can pick. So we'll pick 30, we'll choose all this to be per unit. And let's see how we can now draw everything. Okay, so first is we have to move across the transformer, right? So move across transformer. So let's look at what happens to the base impedance when we move across the transformer. Okay, let's look at what happened to the base impedance. So let's now look at the base. So let's look at the base impedance for zone 2, for the middle zone. This is the base voltage squared over the power base we choose, right? So this is 480 over 480 squared over 30K. This is 7.68 ohms. So let's write down all the base units for all the 3 zones that we have to do calculation with. So let's then write the base 3. This is V base 3 squared over S base. So this is 120 squared over 30. You do this calculation, we get 0.48 ohms. Okay, so the base units are not unitless, right? So the base impedance is still unit of ohms. So only when we divide to get per unit, we have to look at the, let's say, unitless quantity, right? So we calculate the base unit, the base impedance, base current, they still have the normal unit that we have. Okay. So since we need the load current, So let's also compute the base current for zone 3 for the load. Okay, so let's say check. Remember what this equation is? What is the base current value? Remember? So base voltage, base impedance from last time is V squared over S over power. Then what is the base current?
S base over V.
Right, S base over V, right? So it's what you think, it's basically what you think the value should be. So this is S base or V base at zone 3. So we get divide this, we get 250 X. Okay. So again, this problem basically reinforces that we have one power that's consistent for the entire system. The base power is the same. For each zone, we have different base current, base voltage, and base impedance values. Okay, so I think remember the only thing that's the same for the entire system is base power. Okay, everything else depends on which zone we're in, depends on the base voltage we're living. Okay, so this is an easy mistake to make. Sometimes we tend to assume that all the base voltage are the same or base current are the same. That's not the case. Okay, only the base power the same for the entire system. Everything else depends on them. Okay, so now let's look at the impedance. Okay, let's look at if we need to. Oh, okay, I need to add a slide here. Okay, so now let's at each zone. Okay, so for zone 1, for transformer 1, we have 0.10 per unit. Okay, we have something that's value of 0.10 per unit. But now we're looking at going cross zone set, right? Going cross zones. We're drawing a new circuit. Okay, we're drawing a new circuit that should basically let us ignore all the transformers in the system. So does this value change? Does this value change when I draw my new circuit? So my new circuit still has a generator, right? Still has this voltage generator at this side. Now my first impedance is here. If you look at the old diagram, it has a value of 0.1 per unit. So when I do all this, base conversion and stuff, does this value change? Why not? Right, so we have this impedance here, right? So if you look at this impedance, this per unit, this value is computed. So this value is computed from base units of T1, right? We'll compute this from base unit T1. If you read the data sheet of this transformer, it tells you it's 0.1 per unit based on the per unit values of transformer 1. But for this case, we pick the base power to be the same as transformer 1. We pick 30 kVA in this case. We pick the base voltage on this side to be 240 volts, the same as T1. So for this impedance, when we draw it in our now per unit circuit, this does not change. Okay? So this is still J 0.1 per unit, right? So this does not change. This is consistent. We did not need to, a space unit did not undergo any changes. Okay, so this is fine. Okay? This value is fine. All right, is this okay? Okay, so let's look at T2. Okay, so let's look at T2. Let's see what happens to T2. Okay. So T2 had an old value of also okay, so T2 had a value of 0 point. Let me draw this correctly. Let's see. Okay, so let's look at the line impedance. Let's look at this value for the line. Okay, let's look at this value for the line. So for zone 2, for zone 2, we have the value was 0.2, 0.2. So the O value 0.2604 per unit. Okay, but now we're undergoing a change of basis, right? We're undergoing a change of basis. Okay, so we're undergoing a change of basis. So wait, sorry, I think I read this example wrong. Okay, sorry about this. I think we have to redo the example. I think I read the values in the problem wrong for this question. So so this is my fault. So let's not. So I think I need to redo this example. Okay, so sorry about this. So let's skip this for now. During the break, I'll check this. I will redo this example. I think I copied the wrong diagram. I think I copied the answer rather than the question. So I'm confusing myself at this point. So sorry about this. Yeah.
I think the circuit is one slide before that. The question.
Yeah. So I think I copied the wrong circuit. So now I'm very confused by myself. So I think I basically gave the answer, except so then I'm trying to do more calculations. So sorry about this. So let's skip this for now. I'll come back. So during the break, I'll copy the right diagram, and then we'll come back to this. Sorry about this. Okay, so let's skip this question for now. Yeah, somehow copy. I try to make the life easier by copying a diagram, but I think I copied the wrong diagram. Yeah, sorry about this. So let's skip this and we'll look at three-phase. Okay, so we'll look at three-phase, then we'll come back and look at that question, that example for later. Okay, so three-phase, this is chapter 3.4. Okay, so this is chapter 3.4. So for three-phase, so does anybody remember the different types of connections we have in three-phase? Right, there were two connections we had in three-phase circuits. Let's remember what are the names for those two connections?
Y and delta.
Y and delta, right? We have Y. So the first type we have is Y to Y. Okay, so Y to Y is this is one side of Y connection, and the primary and the secondary are connect the same. So this is a Y-Y connection. This is a Y-Y connection. And then if you want to draw this, we can draw, sometimes you see a symbol like this. Okay, a symbol like this. Because for a balanced three-phase, we should have no return current, or the return current is 0. So we can draw this point as ground. Okay, we can draw this point as ground. So for a Y-Y connection, are the primary and secondary voltage in phase? Are they in phase? Right. So for a Y-Y connection, these are in phase. So the primary and the secondary are in phase. Okay. So this is just works as a normal transformer. Okay. So there's no phase change from primary to secondary. The next one we have is a delta-delta connection. Okay. So it's a delta-delta connection. So this is our YY connection. We can have our delta delta connection, where the lines are connected. Like this. Right, where both sides are in a delta connection. Okay. So this is our delta delta connection. And for delta delta connection, again, the primary and secondary are in phase. Okay, there's no phase change between the primary and secondary. Okay, so it's again operates like a normal transformer, like a single phase transformer, except with some factor of √3 in front of it. Okay, so this is the same as single phase. So if I want to change phase between the primary and secondary, what I can do is I can do a Y delta connection. Okay? I can connect one side in a Y, one side in a delta. This is fine. Okay? You will see this connection in practice. This happens. And when connection like this, are the voltage in phase? If you have a Y delta connection, are the voltage in phase?
No.
So how much difference do they have? What is the difference in angle? So my high side is Y. Let's say the primary side is Y.
Sorry?
Sorry?
Is it 30 degrees?
Yeah, they're 30 degrees apart, right? So Y leads delta by 30 degrees. So the voltages are not in phase anymore. Because the line-to-line voltage becomes a phase voltage, right? So that's why they're not in phase anymore. And there's a 30 degrees difference. Okay, there's 30 degrees difference. Okay, so three-phase transformer, really the tricky thing happens when we have different types of connections at the primary and secondary. Otherwise, it's as if we have a single-phase transformer. And the only change the only thing we need to be worried about is when we have this sort of Y delta connection. Otherwise, it's just the same as before. Okay, so if you think about it, which connection do we see more often in practice? So this is a practical issue, but I think about in practice, do you think we see YY a lot, delta delta a lot, Y delta a lot, delta Y? Which do you think we see a lot?
I think delta delta.
So delta delta we do see a lot. Okay, delta delta we see a lot. Many connections are delta delta. Why don't we see YY a lot? So it's an interesting question to think about. Why don't we see YY? You would typically do not see YY connection all that much. Okay, I think a reason why Y to Y is not very common. Okay, so here we said, so Y to Y is not very common. Okay, so here it says third harmonics can be a problem. So why do I think, right? So on the chat says YY needs a grounding wire, right? So if you think about when we taught, when you're taught about transformers, what we said is if it's balanced three phase, then you don't need a common ground, or you don't need a return wire. But often in practice, you're not exactly in balance. It's hard to say these three phases are exactly in balance. That the angles are exactly 120 degrees apart. The voltage magnitude are exactly the same. So when you don't have things that's exactly the same, so if the three phases are not exactly the same, then this thing in the middle is not zero. It's not zero. So you basically have three slightly different sinusoids adding to each other. And this causes something called a higher order harmonics. Okay, this is called higher order harmonics. The higher order harmonic comes if you add sinusoids with slight difference in phase and magnitude, then they're not exactly in phase. So you don't have 60 hertz things exactly. And then you create some harmonics. And for this case, it's some of the higher order harmonics that tend to get amplified if you're not exactly in phase. Okay, so you don't see Y all that much. Delta is more robust on this side. Okay, delta is more robust. Okay. So, and for generator connections, what you typically see is, so we have a generator to a line. What we do is you have a delta on the generator side, because for the generator, it's hard to run a grounding wire. Okay, but this being a delta is better for higher order harmonics. Then on the transmission line side, you have a Y and we add a grounding wire. Okay, so sometimes we just ground the neutral, right? So on the transmission side, we can ground it. So if there are harmonics, there at least somewhere somewhere can go. And then for the generator side, we have a delta connection. Okay, so you see delta Y. So for generators to high power transmission line, you see a delta Y. And then for lower voltage or comparable voltage, you see delta going through. So that's the practical way when this kind of transformer are connected. Okay, any questions about this kind of connection? So if you ever work on transformers or in the utility, you see more delta than Y. You see a lot of this sort of delta connection. Okay, so let's look at how we do the calculation. Okay. So the goal is always the same, right? So the goal for three-phase is the same as for single. So per unit three-phase, again, to make everything look like a single-phase circuit. Okay, we want to pretend everything is a simple single-phase circuit. Okay, that's what we want to do. And the way to do it is to make sure, again, we take care of factors like this. Okay, so let's make sure that the root 3 goes to the right place, the angles goes to the right place. So again, we can just write down the circuit without worrying about the fact that we have a three-phase transformer. So that's, again, our goal. Right, so we know the line to line to neutral voltage works like this. But this, again, not nice. Because if we have a difference between line to neutral, then we have to care about how the transformers are connected. We have to think about the different connection. We have to always carry a root 3. So during the 351 class, at least when I taught it, a lot, 20, I think 20, 30% of the grid is lost to not handling this root 3 correctly. So this is a major issue of something going wrong. So what we would like is, we would like to have these two to be equal to each other. Okay? We would like these two to be equal to each other. So I don't have to worry about whether it's line to neutral or line to line. Right? So we want our per unit system again to make this happen. Okay, again to make this happen. And this is again not very hard to do. Right? To do this is all we need is to choose a base unit that has the same factor. Okay, so if it's if we're talking about line-to-line voltage, then let's use a base unit. Let's make sure we choose a base unit that's root 3. It has a root 3 factor already built into it. So when we do the calculations, we don't have to worry about this root 3 anymore. Okay, right? So in a three-phase system, so this is we want to choose. Okay, so we basically wanted to pick. We want to pick the voltages correctly. We want to pick the base to already have this root 3 factor built into it. So during calculations, I don't have to worry about this anymore. Okay. All right, and then same thing. We want to do the same thing for power. Okay, we want to do the same thing for power. Right, so we want to do the same thing we know for a three-phase to single phase, there's a factor of 3. in front of three-phase to single phase. So but in per unit systems, we want them to be equal, right? So we want in per unit systems, we don't have to worry about the number of phases or how they're connected. So again, what we can do is we can choose the per unit system to already have the three built into it. Okay? So these are sort of the obvious things you should do. And we do this obvious things, we make these type of choices, then this will be correct. We do a circuit analysis, everything will be simple. Everything will be simple. So we have this, so we choose the voltage base units to have this relationship. We choose the power base units to have this relationship. Then let's look at what, how does this imply for current? Okay, for current and impedance. Right? What happens to the current? What happens to the impedance? Okay, so let's look at what happened to the 3-unit current, right? So we make this choice. Okay, we make this choice. And what we want is for this equation to still hold. Okay, we still want power to be the voltage per unit times the current per unit. Okay, so let's see what this implies. So this implies that the power divided by the base unit for three-phase power. What does this equal? Well, this is line to line times current. Okay. I say we have this. And we want this to be base times current base. Okay. This comes the current base unit. Okay, so this is implied. So how do we choose the current? Well, we should choose this current to be the base unit over √3, the base voltage line to line. Okay, so we want to make the current choice this way. So the equation now makes sense. So when you substitute this back in, we get so this should imply each other, which gives us, this is our current base unit. Okay. So it's the total power for the three-phase system divided by √3 times the line to line, divided by √3 times the line to line voltage. Okay, so this is what we want of the current base units. Then we can do the same calculation for the impedance. Okay, we can do the same calculation for the impedance. So for the single phase, what we have is the line to neutral voltage equals to the single phase impedance times the line current. And we still want Ohm's law to hold. Okay, we still want Ohm's law to hold in this case. So here what we have is we want the line to neutral voltage divided by the base line to neutral voltage. Okay. So this, by definition, is a single phase impedance times the base impedance times the base current. So we rearrange this equation. What we get is this should be the base divided by to line divided by √3, the power for three-phase divided by √3 times power for line to line. And this is what we have. Okay, so this is the expected equation we have. So again, it works out that we pick per unit system correctly, right? So we pick basically the voltage at the rated voltage, pick the power correctly. What we get is then the base impedance is just the base voltage squared divided by the three-phase power, divided by the three-phase power. Okay, so these are sort of the expected ways these base unit will work out. Okay. And the way to do this is just remember these equations, right? So you don't want to derive these in real time. You want to save yourself some effort. You want to save yourself some effort. So the way is just to remember these equations. Okay? And the process for the circuit is we're going to choose, again, a base power arbitrarily. Okay? Then for each voltage level, choose the base voltage, choose the base voltage as a base line-to-line voltage. Okay, always choose the base voltage as a base line-to-line voltage. Then base current becomes this equation, and base impedance becomes the equation following that. So this is just a recipe to do calculations. And for three-phase boils down to, pick a power, remember these are the equations to use. And then we can do all the calculations pretending it's a single phase circuit and not worry the fact that it's a three-phase circuit again. Okay, we just pick, once we pick the base units, and then we'll just go on with a single phase circuit calculation, okay, and not worry too much about where this comes from. Okay. So any questions about this? So again, the important thing is to remember these equations. The important thing is always remember basically the equations on this slide and follow the recipe when we do the problems. Follow the recipe. And the reason is if you follow this recipe, then things will work out. Basically, we build in, where the root 3 should go, right? We build in how all the base units should work out. Okay, so that will, and we should, if you follow this convention, things will work out. Things will work out if you follow this convention. Right, so it's important to know where to find these equations. Okay. And again, you want to avoid deriving. You want to avoid deriving all these things in real time. Any questions with this? So this is again similar to single phase, except that the equation is somewhat more complicated. Okay, except we have a more complicated equation.
Professor?
Yeah.
Can I go back to the one slash up?
Sure. This one? Impedance?
Yes. Thank you.
Yeah, so this is just impedance equation. So root 3 cancels out at the right places. Right? So we have root 3s, but we'll cancel out at the right places. Okay. So let's do one example. Okay, so this is 3.5. Hopefully I copied this thing down correctly. Okay. So we have a Y to Y, right? So we don't see Y to Y often in practice, but in homework, you do see a lot of Y to Y connection because this is the, so we see, I say we have this kind of connection. Okay, and so let's say this is our example. Okay, so this is our example. So let's see. So here we have Y to Y. We have a ZL. This is balanced three-phase 185° omega. We have ZY given 1040 degrees omega. Okay, so this is our example. Let's look at the voltages we have. Okay, so let's look at voltages we have. So we have a input voltage face to face of 480 angle 0. So we'll apply face to face 480 angle 0. And here what we want is what we have is now we have the rated power, the base power is three-phase. This 10 kVA. This rated power is 10 kVA. And we choose a base line-to-line voltage to be 480 volts. Okay? So we have this circuit, and we want to convert this to a normal single phase circuit, right? We want to convert this to a single phase circuit. Okay? All right, so let's do the conversion to a single phase circuit. Okay, let's do this conversion. So let's look at the base impedance for this circuit first, right? So let's look at this bunch of equations. Okay, so we're told what the choice for the power is. We're told what the choice for the voltage is. For this example, we have impedance given in ohms, and we want to convert this to per unit, right? We want to convert this to per unit values. Okay, so let's convert these to per unit values and see what they are. So let's do the base impedance base calculation. So you come back here, you look at this equation. This tells you it is the 480 squared divided by the base power. So this becomes 23.04 ohms. Okay. Right. This is just our base impedance. Then let's look at what happened to this part. Okay. So we have the L per unit. This is just the L divided by the base. So this becomes 185 degrees over 23.04. And this is 0.043, 85 degrees per unit. Okay, so the angle again doesn't change when we have a per unit calculation, and the magnitude changes like this. Okay, so we have the Y per unit. This is 10 angle 40 divided by 23.04. So this we get is 0.43 angle 40 per unit. Okay. For this case. All right, so these are the per unit system, right? These are the per unit system, per unit impedance on both sides. So now let's do the following, right? So let's see. Let's say what is the per phase voltage? Okay, let's look at what is the per phase voltage. Here we're given the line-to-line voltage is like this. Okay, the line-to-line voltage is 480. So how do we convert that to the per phase voltage? How do we convert that to the per phase voltage? So what is the base, for example, for the line to neutral voltage? If the line to line is 480, how do I convert the line to neutral voltage? What do I divide by? So which is higher? Is the line to line larger or is the line to neutral larger? For voltage magnitude. I remember from before?
Line to line.
Line to line.
Line to line is higher, right? Line to line is higher. So what we have is, so we have the base line to line divided by √3. Okay, so this gives us the line to neutral. Okay, this gives us the line to neutral base. So we have 480 divided by √3. This gives us 277 volts. Okay. So let's put this in per unit terms. Okay, let's put this in per unit terms. Okay. So we need to divide the voltage by the base voltage. Let me continue here. So to finish the circuit, I need to divide the voltage by the base onto neutral. So what is the per phase voltage then? So if the line to line, right, so we're given EAB is 480. angle 0. Then what is the AN? What is the phase voltage in A?
277.
277, what is the angle?
Unchanged.
Is it unchanged?
Or sorry,
right?
negative 30.
Negative 30, right? So negative 30. Right? So this is what we have, right? So the angle changes, we will convert line to line to per phase, right? So if the line to line is angle 0, and the per phase voltage is minus 30. Okay, this per phase is minus 30. So this 277 angle minus 30 divided by my base units. So this is 1 minus angle 30. Okay. So if we draw the single phase circuit, what we have is a generator. So this is a single phase or the per phase circuit. 1 angle minus 30. Everything else is in per unit. So they have some impedance. I have some load here. This is 0.043 angle 85. This is 0.43 angle 40. Okay. So this is our equivalent circuit at the end of the day. If we write everything per phase and per unit terms. Okay. So we end up with this circuit. Any questions with this one? So the important thing is to remember there is a angle. Okay, so when you go from line to neutral, there's an angle shift. There's a 30 degrees angle change. Okay, there's 30 degrees angle change, right? So before when we're doing in class exams, you sort of have to have a fairly good idea, memorize this in a fairly good idea. How do we do this? Where does the angle go? So now you can just know where to look up this angle changes. But do remember there's an angle shift, right? Since in this problem explicitly we give that the line to neutral, the line to line is angle 0. So the line to neutral is not angle 0 anymore. So it's minus 30 degrees. Okay. So we'll do, right, any questions?
I had a question. On the page above this, I just wanted to confirm on the right side where you get the answer ends up being 0.43 angle 40. Was that ZY per unit?
Yeah, this is ZY per unit. So let me rewrite this better. This is ZY per
Okay.
unit. Yeah.
So when you're summing these up, how come we can kind of sum like 3 different impedances into one? We sum all 3 of the Y connected impedances and all 3 of the delta connected impedances into one.
So we don't sum, right? We're not summing. We're doing this. We're saying this is equivalent to 3 per phase circuits like this, right? So we're not summing this. So here we already have a YY connection, right? This is already a YY connection. So for each phase, we have a ZY. And this is balanced 3 phase, so they're all equal value.
So we would actually need 3 of the per phase to represent this though.
Right, so this circuit is equivalent to 3 of these, right? So this is the per phase per unit.
Yeah, okay. I mean, that makes sense now. Okay.
Yeah, so there are 3 of these, but they're exactly the same.
I see.
In this.
All right, thank you.
Yeah, right, so that's a good point, right? Yeah, I should make that clear. So it's not the 3 phase one becomes a single phase circuit. There are 3 of this one, but they all look the same. So when we do calculations, we'll just do it with this one. Right? When we do calculation, we'll do it with this one. Okay, so when we need to compute the current, we'll compute the current. For the other 2 phases, they're equivalent, right? They're all identical, basically, in this kind of diagram. So we only need to work with one of them. We don't need to work with all 3. Okay.
So when you'd be computing the current for that, would you find the current in this per phase and then multiply it by 3 to get what would be the real current on
Okay, right. So the key conceptual thing is there is no notion of real current, right? Right. So let's think about what current means in this Y-Y connection. So what is the total current for a balanced Y connection? What is the total current if I sum to this point?
0.
0, right? So we don't sum the current because there's a per phase current, right? There's per phase current. But when you sum all the current, it's actually 0 for a balanced system. So we don't need to talk about the total current in the system.
Okay.
There's not a notion of total current. Even total impedance is a little bit misleading. Right? So when we talk about this circuit, we can talk about the per phase current, per phase impedance,
yeah,
and the total power, right? So the only thing we sum is the total power. It's 3 times the per phase power. So this is the only times we sum. Right? So only when we come to the power, we'll multiply by 3, and that's the total power. For the current, since the net current is 0, then we don't really talk about. But the impedance is easier to talk about per phase. This is the impedance, not really the total impedance. A little bit misleading. We talk about that, right? So that's a good question. Yeah, good question.
Okay, thank you, Professor.
Yeah, no problem. Yeah, so that's a good question. Right? So please, you have a question like that, please ask. Right? Again, this is important conceptually, right? So when people say total current going through a balanced 3-phase system, not really a meaningful thing to talk about, right? So normally when people say, even people say current through a per phase system, 3-phase system, is probably the per phase current, right? Probably per phase current. When we talk about power through it, there's a notion of total power. We'll add the power, talk about total power. Right, so let's do one last example, and then we'll break. Okay, so let's finish the last example we have for this, then we'll do a break. So let's do one last example for the 3-phase transformer side. So this example is we're gonna have a 3-phase. So this is all 3-phase. Okay. We have a line-to-line voltage 220 kV. We're sending power and we're converting it to something else. Okay. So we're gonna choose this base quantity, and we're gonna try to ask what is the receiving end voltage, what is the receiving end power, what is the receiving end power. So basically here we're trying to go from per unit to absolute value, then coming back to the SI value again. Okay. So we're going to do this conversion just to see this one more time, right? To see this one more time. Okay. So we're going to choose and to do some power calculation. Okay. So we're going to choose the base to be 100 MVA, and choose the base power to be 100 MVA, base voltage to be 220 kilovolts. Okay. They're going to choice we're going to make. Okay. So right. The reason we choose 100 MVA is, you know, there's 70 and 30 MVA in the powers to generate sending, so we're going to add them up, call it 100 MVA. This. So, you know, one thing is choose a nice round number for this kind of power base, right? Don't choose something weird like 89. People have done in the past, right? So choose some round number. And let's do all this calculation. So we have a transmission line that has some impedance per phase. So let's do a base calculation of what this should be. So let's do this. So let's say the base. We're gonna do the V base squared over S base. So this is 220 kV squared 100 MVA, 44 ohms. So this is our base. Right, so let's do this conversion. So we have, so when we do the conversion, basically we'll divide them all by the base units. Okay, so our conversion is very easy. We'll divide everything by the base units. Right, so when we divide things, voltage is 1 per unit, divide the power, 70 divided by 100, 30 divided by 100, divided by Z. So, so once, as a reminder, we can write down the base unit we have used. After that, we're going to just divide. For ohms. Okay, we'll divide this. So we'll get everything per unit. So now we want to do the calculations per unit, right? We want to do all this calculation per unit. So now let's do the current calculation in per unit terms. Let's do the current calculation. So there are several ways we can do the current. Okay, there are several ways we can do the current. So here we're gonna do, so here what do we know, right? So let's look at what we know. We know the power coming out of the generator. We know the voltage. Okay, we know the voltage phasor and we know the total power. So the way we do the current calculation is we'll use this equation again, right? So the power we send is equal to the voltage phasor times the current phasor complex, okay? Times the current phasor complex. So the current phasor conjugate, sorry, the conjugate of the current phasor. So current phasor conjugate is this. So we have the conjugate of the current as 0.7 plus J 0.3, 1 angle 0. So this is very easy division to do. 0.7 plus J 0.3 per unit for current. And we want in polar forms, we'll write this as minus 23.2 per unit. So we'll remove the conjugate. Right? We can remove the conjugate by flipping the sign of the angle. So flip the sign of the angle, we get this is our current. Right? This is plus 23. So I have minus 23 here. So this is the conjugate has an angle of positive 23 degrees. So the actual current has a minus 23.2 per unit angle. Okay, so we can now compute the current. The next step, let's compute the voltage. Okay. So we have the current computation, we'll compute the voltage. And the voltage is simple circuit calculation. We have some source voltage. We now have a voltage drop. Okay, we have a voltage drop across a line. And the voltage drop is given by the current times the impedance. Okay, so this is our receiving end voltage. So this is 1 angle 0 divided by 0.76 angle minus 23.2 degrees times 0.01 plus J 0.24. Do this calculation, we get 9.6 angle minus 0.5, minus 5 degrees per unit. Okay, so this is our per unit voltage. Right, and then the power is again fairly easy to compute, right? If we know the voltage, we know the current, then the power is really simple to compute. We have the received power as the received voltage times the conjugate of the current. Plugging all the numbers, we get point, so this is 96 angle minus 5 degrees times 76 angle minus 23.2 degrees conjugate. We're plugging all the numbers, we get 0.9693 plus J 0.228 per unit. Okay. So these are all the per unit calculations we have, right? So once you get things per unit, then it's pretty simple circuit calculations, right? The normal Ohm's law holds, voltage current power relationship holds, and things like this. And then the last thing is, right, let's convert things to SI units. Okay, so we have solution in per unit. And let's convert it back to SI units, right? So can we write things back to the standard units we have, given these are the base quantities we have? Okay. So if these are the base quantities we have, then what we can do is converting to SI units is fairly simple. So from the source, we have information from before, this 220. The sending end is 70 plus J30 MVA. The line flow current is really simple. You take this base and then multiply by whatever line current we got. Okay, so it's a straightforward multiplication. So this is the per unit current we had, which is 0.76, angle minus 23.2, multiplied by the base current, and we get 199, angle minus 23.2 degrees. Voltage, the same thing. You take whatever voltage we got and multiply by the base voltage. Okay, so this is 0.96, angle minus 5 degrees, multiplied by the base voltage. This gives us 20, angle minus 5 kV. Power, the same thing. Whatever power we got before, 0.963 plus J 0.228. Multiplied by the power base, we get 9.3 plus J 22.8 MVA. Okay. So this fairly straightforward calculation. Right? So the nice thing about this calculation is again that you convert everything to base units, to per unit system. Okay, you do this conversion. Then you do everything per unit. Then at the end of the day, if you're interested in the SI units, it's a simple multiplication back to the SI units. And the nice thing about, again, the per unit system is we sort of know how much voltage drop is, right? So so sometimes the SI units is actually harder to have a feeling, right? In SI units, we know the voltage went from 220 to 211. Now, is that big or small? You have to do one more calculation. But in per unit, we know the voltage went from 1 to 0.96. So this is a 4% drop, which is not very big. Okay, so another thing that per unit system gives us is this sort of feeling for the relative magnitude of things in the system. Okay, it's for this relative magnitude, right? So that's why per unit, often you just see things in per unit. Often we don't even bother to convert things back to the SI units. But if we wanted to, it's just a simple multiplication at the end. Okay, so now let's break. So that's a little bit late, but let's now break for 10 minutes. We'll come back at 10:50, and then we'll do the example which I made a mistake on again, and then we'll go to transmission lines. So any question about homework or the lecture, please you can ask during this break.
So I have a question about. Oh, sorry. Go. You can go first.
You can go first.
Okay, thanks.
Yeah, whoever.
Just a quick question. So
Sure.
in order for a transformer for the per unit system, the reason we can have refer the impedance, regardless whether it's on the primary or the secondary, the reason we can do that is because the rated voltage of the transformer on either side is equal to the base voltage in the per unit.
Yes.
The problem is, for example, like the last one in the homework, or for the example that we started working out, there's a small difference. Like the rated voltage, for example, for the first transformer is slightly large. So the first transformer and the second one, the secondary side rated voltage is slightly larger than the primary side of the second transformer. And so there's that slight difference in rated voltage. And
Wait, so are we talking? So let's look at the homework, right? Let's look at the homework. If this, yeah, for that example, I'm gonna redo that example. So for the homework, is this, which question are we talking about?
Number 6.
Number 6. Okay, so this is figure 2.
Yeah.
Okay, so.
And so transformer 1, the secondary voltage.
Oh, there's a slight difference. Okay, there's a slight difference.
And so now, is it because of that we can't really?
Right, okay.
Set a new.
Yeah, so there's a small, yeah, so that will introduce a small correction actually.
And also,
yeah, so how do we want to do this? So actually, we're going to assume that the secondary for the first transformer is 10 kV.
Okay.
Yeah, that's either. Okay, so I will make the change. I'll update the homework right away after this lecture.
And
this was harder than I meant it to be.
Sorry, one more thing. And the motor and the transformer 2, would we also make the motor 5 kV? Or would it not matter actually?
For which question? Sorry. Question
number 6, except the motor. Actually, we would actually use the change of base formula, correct?
Yes. Yes.
Okay.
Yeah.
Okay. Thank you.
Yeah. So I'm going to have the secondary for T1 to be 10 kV. Yeah. This is come out harder than you thought.
Hi, Professor.
Yeah.
I got some question for the problem 6.
Mm-hmm.
I got some question for the problem 6.
Okay.
And
same question. Yeah.
Yes. For the T1 is the turn ratio is 2400 to the 9600.
Yeah.
And the T2 is 100,000 or one like the 10K to the 5K. And the turn ratio is different, and one's the 9600, another is 10,000. So I think I can just assume like for the base voltage in zone 2 is 9600. And
right. So the 9600 is not 10 kV, right? So I think that's the problem, right?
But for the base voltage in zone 3, it can change to be the 4800 instead of the 5000.
Yeah. So let's see.
So in this case, as the base voltage 2 and the base voltage 3 has a turn ratio the same as the T2.
Yeah. So I will update the problem. So I will update the T1's secondary voltage to be 10 kV, and I'll make the motor 5 kV. I'll make the motor 5 kV.
But what's the difference making the motor be the 5 kV? Because we only calculated the power.
No, so the motor has a rated voltage, right?
Yes.
The motor has a rated voltage, so you don't necessarily need it because the motor doesn't have an impedance.
Yes.
Right, it doesn't have an impedance, but I think it'd be less confusing making all 5 kV.
Yeah. I think I found a solution for this one. For the zone 3, I just changed the base voltage to 4800 instead of 5000. That could solve the problem.
Yeah, you can do that. You can do that, but yeah, this is more difficult than I want it to be.
Oh, yeah.
So if I've done it that way, that's fine, right? You don't have to change the solution. If you've done it that way, that's fine.
Yeah.
But if not, I'll make the question more consistent.
Sure. Thank you. But for the motor, this one, it doesn't matter. It's a change the base voltage. We only
for the motor, So for the motor, it doesn't have impedance, so that's fine.
It's just 25 kVAR over the base, like the 100. That's what we got.
Yeah.
All right. Okay.
So yeah, so this is entitled. Okay, so first announcement about the homework. So for problem 6, figure 2, the values makes the problem harder than I want it to be. So you have already done it, then that's fine. You don't need to change it. But then if you haven't done it, I'll update the homework after this class. Basically, the secondary for the transformer 1 will be made into 10 kV. So it's consistent with the transformer 2, right? With the primary of transformer 2. Okay, so you haven't done it, just wait a little bit until this is updated. We have done it, and you found a way to deal with a slight difference in the voltage level, that's fine. You don't need to change. You don't need to change your solution. Okay, so just hold off a little bit for that homework question. You haven't done it. Okay, so any other question about homework, I guess? So let's do this if everybody's here. Okay, all right, so no question about homework. Let's do the example 3.4, which I completely messed up at the beginning of the class. So as a redo, basically I copied the wrong figure. Okay, so now this is the correct figure we're gonna look at. Okay, so the SI unit figure, this is 20 volts. We have a generator connect to a transformer. Through a transformer, connect to a transmission line, which is some impedance, connect to another transformer. Then we have the other side. Okay, we have the other side of the load, and this load is piece of load. This is 0.9 plus J 0.2 ohms. This thing is 2 ohms. So, and this transformer is 30 kVA, 240, 480. This is 20 kVA. So here we see a slight difference of the voltage levels, right? So let's see what this does. 115 volts. Okay, so this is the original problem. And here the equivalent impedance referred to the primary. This is 0.1 per unit. Here the equivalent impedance referred to the primary. This is 0.1 per unit also. Okay, and our goal is to draw a single phase circuit or draw a per unit circuit to deal with this problem. So let's look at what we do again. So let's as a redo, let's pick this power base to be 30 kVA. Again, let's pick this to be 30 kVA. And we're going to pick different voltage bases, right? So we're going to pick the voltage at base 1. This is 240. Voltage base for zone 2, this is 480. Voltage base for 3, this is, I'm going to pick this to be 120. Okay, 120 volts. Okay, so then we can work out the impedance for all 3 zones. So impedance for base 1, this is the V squared over power. So this we get is 1.92 ohms. Base 2, same equation. We get 7.68 ohms. Base 3, we get 0.48 ohms. Okay, there we get 0.48 ohms. Okay, so now let's, for the per unit, let's see what happens. Okay, let's see what the per unit thing happens. Then we have the X equivalent for transformer 1. For transformer 1. This again doesn't change. Okay, this becomes still 0.1 per unit in the new circuit. Because which the voltage and power base is the same for transmission 1. Sorry, for transformer 1, the voltage and power base are the same. So this per unit doesn't change. Okay, but then we need to do a new one for transformer 2. And for transformer 2. Okay, so we need now to do a conversion. Okay, we need to do a conversion. So let's say xt2 per unit is the old value multiplied by the old base divided by the new base. So if you look at the equation from last class, divided by the new base times the new power divided by the base for the old power base. So plugging all these numbers, we get 460. So if you look at the transformer rating, is given at 460. So this per unit is referring to this base voltage. It's referring to that base voltage. So we want to put this into the new base, which is 480. So we're going to divide by the new base squared. Then if you look at the new power is 30 kVA, but the old power for this transformer is 20 kVA. So there is a third changing the power base as well. You multiply all this out. This is 1378 per unit in the new thing. All right, so this is our new per unit value. Then our line in per unit, this is just the SI value divided by the base value. So there's no conversion here there's no base conversion here. Divided by 7.68, there's 0.2604 per unit for the line. Okay. And the load per unit is the O load divided by the base zone 3, so 0.9 plus J 0.2 by 1.48. And this is 1.875 plus J 0.4167 per unit. All right, so this is our new circuit. Okay, so this is what I wanted to do for this circuit. So you look at the new circuit, right? So basically, also let's do the voltage conversion. So for voltage, right? For voltage, V1 per unit, this is 220 angle 0 divided by the base 420. This we get 0.917. So our new circuit is this with impedance, with another impedance, with a base load, connect to ground. This is 0.917 angle 0. This is 0.1, 0.02604, and this is, what was the line? Yeah. This is a line. This is transformer 2, so this is 0.2604, 0.1378, and the load is 1.785 plus J 0.4167 per unit. Okay. Right, so this is the value. This is the per unit diagram that we have. Okay, this is our per unit diagram. Okay. So here we do have a case where the voltage are slightly different. And what comes down to is here we choose 480 to be the both base voltage for zone 2. Right? We could have picked 460. Okay, we could have picked 460. So this is a little bit ambiguous what you should have done for this part. So if you look at the homework, the current homework have similar issue. Basically, you can pick either of the voltages as both ends. So you have already done it this way. If you already pick one, that's fine. You don't need to change it. But to make life a little bit easier and to have a unique answer, we haven't done the question for in the homework problem 6. We'll update the parameter. We'll update the parameter to make it more consistent. Any questions about this?
Professor, I had a question.
Sure.
Why did you pick 120 for base 3?
Oh, so I could have picked 115, but we like round numbers for base. So we almost always pick standard numbers, right? So 120 is a more standard number. 240, 480, these are standard numbers. So we like to pick standard numbers for base. But this is not necessarily obvious as you're doing homework. So we should, yeah, so 6, so that's why I want to update problem 6 in the homework. And let's make it a little bit less ambiguous what number should pick. And but in practice, we pick nominal numbers as a base. We like to pick nominal numbers as a base.
And you're saying you just picked 480 just to make it a little bit different?
Yeah, it's a multiple of 120. So we
okay.
we have 120 volts, we have 240.
Right. Okay. Yeah.
Right.
Yeah.
Then so if you look at the Corey building, right? It's not Corey building. The ECE building we have, that's 480, right? So it goes out multiple. So it just goes this way. That's why we pick nominal base voltage this way. Right? But this is this convention. Yes. Go ahead.
Hi, Professor. I think
Yeah.
the reason we choose the 120 volt for this one, for the base, is because of 480 over the 120 is the same turn ratio as the T2.
Yeah, so that's...
It's not just the arbitrary base. Because 480 over the 120 is the same as the 460 over the 115. So they have the same turn ratio.
So it has the same turn ratio.
That's sort of actually my follow-up question.
Yeah, okay.
That's sort of my question is, because if we don't choose our base voltages as the rated voltages, or at least as the ratio of the rated voltages, then we can't really do we can't really get rid of the transformer, because the per unit on one end will not be equal to the per unit on the other if we don't make the base voltage the same as the rated voltage on that end of the transformer, or at least equal to the ratio. Is that correct?
No, I don't think because no, the issue is there that your turns ratio may not need to be the same, right? For example, you can step it up to 480, but you can step it down more, right? So suppose I want to step down to more. I may not always have a 4 turns ratio on both ends. Right, so I don't need to step. So here basically oh, I see. Okay. Right. So, okay. Yeah. I see. Yeah. So 120. Yeah. So all right. So the turns ratio should be consistent with 120. Yes. 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 I think you guys are correct. Yes. So since the T2 is stepping down by N1 over N2 of value 4, so we pick the base voltage for the middle. We should divide by 4 to pick the base voltage at the end. Yes. Yes. I think that's correct. Yes. I think that's also correct. Yes. So here is, so right, so this is, okay, so let me add something. Okay, so we pick 120 because 460 over 115, this is 4. So 480 over 120, also 4. So we need this turns ratio to be consistent. I think you guys are right on this. Yes. Yes.
So you have to pick 480 because 460.
Yeah, I think, yeah. So once we pick 480, we have to pick 120. I think that's the way to
But
understand.
could you have done the problem at 460 and 115? You couldn't have, right? Because it wouldn't have matched.
So we wanted to do the problem at 460. Then we need to look at the base voltage for.
We need to change the base voltage.
We need to change the base voltage for zone 1.
Yeah. Okay.
Right. So we need to divide that. So we need then 115 should be the base voltage for zone 1. We could have done that way. We wanted to. Right. I think so. That's a consistency. Yeah. So I think this is a good reason. I think this is a good point. So since we pick zone 1 to be 240, then everything else is determined by the turns ratio. Right? We pick zone 1 to be 240. Then we need a zone 2 to be 480. And that goes down the chain. Nothing goes down the chain of the transformers. Yes. Yes.
Hi, Professor.
Yeah.
Can I see the equivalent circuit, the final equivalent circuit?
Sure. Yeah.
All right, thank you.
Yeah. So I think that's a good point. Yeah. So once we pick 240, then we set on 240, then 480 has to be the choice, and everything else determined by the turns ratio. So Yeah, so let's see the homework. Yeah, so let's make things easier to make the voltage the same. To avoid ambiguity, which side we should pick. Yeah. Because it's a little bit more difficult if we have a cycle that is not clear how this kind of sequential choice, how does it come back? Right. So now, to make things easier, let's make I'll make the homework, the voltage to be the same on both sides. Okay, so that's yeah, that's a very good point. Okay, so there's slightly more complicated transformers we can make. So these are more for curiosity than doing calculations with. Okay, so for example, if you want to save some cost, you have a 3-winding transformer. Basically, you can have 2 windings on the secondary side or on the primary side. Right, so they don't have to have the same turns ratio. Right? Then that's not necessary. So you can get a substation to output many levels of voltages on the secondary side. So that's definitely possible to do. And then this basically makes the practical transformer model more complicated. And this makes the practical transformer model more complicated because the circuit, the non-idealities become more complicated to work with. Okay? But you do have substations with this kind of connection. Okay, so this happens for bigger transformers when you need 2 things to come out of it. Then another thing that you may see in practice is something called auto transformer. Auto transformer basically says you're going to tie 2 things together. Okay, auto transformer basically shorts the secondary side, the ground on both sides together, right, to make a higher voltage. And sometimes we see this kind of auto transformers. Right? So, but this is again something that's sometimes used to save cost, make things cheaper. Okay, all these sort of changes make things cheaper, but we won't really cover this in class all that much. We won't cover this in class. Okay, so, and there are things, with interesting things that, doesn't give you a fixed ratio turns. Okay, there are things that doesn't give you fixed ratio turns. Basically, what happens is, if you have a transformer, often as you want the secondary to be a little bit more flexible. So what this looks like is the primary is whatever the primary is. In the secondary, what you want is you want to have multiple voltage levels. Here you want multiple voltage levels. Okay, so this can happen in practice. And this happens for a distribution system. Okay? And so let's think a little bit about why this happens, and we may come back to this later when we look at voltage stability toward the end of the class. Okay? So if you have a distribution system, say this is your substation. Okay? So this is our feeder. Distribution system means this is a residential network. So it looks something like this. Okay, these are sort of houses. You can think of different loads attached to the system, different streets. This follows fairly close to the topology of the residential street. Okay? So this is a network. So what happens is, let's say you start off with a 1 per unit voltage. You start off with 1 per unit voltage. What happens by the time you get to the end, this voltage tends to not be 1 per unit anymore. Okay, so if you have a circuit and you have things in the middle that draws power, what does the voltage do to get to the end? So you have a long circuit, you keep adding load in the middle. Then what happens to the voltage? Anybody have experience with this? So very long circuit. So what happens as n to the voltage is this voltage. So this voltage is low voltage. But this, how low those voltage goes depends on how much load you're drawing in the middle. Okay, so if you're drawing a lot of load in the middle, this voltage is very low. if you're drawing not that much load in the middle, maybe these people are not at home, this voltage is fairly high. So there can be different levels of voltage we have in the system. So then what you do is we may add a tap changing transformer. So add a transformer. And what this transformer does is, depending on how much load we're drawing, this can have a rated voltage of 1 per unit, maybe something that goes from, we can step it down to 1 to something like 1.2. Right? So if the load is not very heavy, it's just a 1-to-1 transformer. It doesn't do anything for the voltage. But the load is very heavy, we'll step up the load. So it's okay by the time we get to the end of the feeder. So almost every distribution system have this sort, will have a tap changing transformer. Because the environment changes and the turns ratio may not be constant, depending on the environment, depending on the load in the system. So this is a tap changing transformer. And it's really a mechanical system. So you have coils, and you have a mechanical device that's attached to different levels of the coil, right? To change the turns ratio up and down, okay? So this we can have this kind of transformers. We can also have something called the phase shifting transformer. A phase shifting transformer is, for normal transformer, ideal transformer, the phase doesn't shift. It's the same phase from primary to secondary. But in practice, we may want to shift the phase a little bit in practice. Okay, there are situations where we do want to shift the phase. And then we need to engineer a transformer that actually does this kind of phase shift. Okay, we may need that in a actual large system. So later in the course, we may look at this kind of, we'll look at this kind of transformers. But for now, most times we'll be dealing with sort of a practical transformer, but still something that has a constant turns ratio. So that turns ratio doesn't change from time to time. And that something doesn't shift voltage. Okay. So any more questions about transformers? All right, so we have a little bit of time left over. We'll get started on transmission lines. Because I want to get to the point where I want to give us an idea where we're trying to go for transmission lines, right? Not necessarily, now the math in transmission lines, so this is chapter 4. If you look at chapter 4 now, you may not like it very much. It seems there's a lot of path integrals in that chapter. There's more vector calculus than probably you have seen or you have remembered. So I want to say what we're trying to do. Okay, what we're trying to do. So transmission line by itself, that's an interesting object. There's actually a lot of electromagnetic calculation you can do with it. But what we're trying to do for this class, through the next 1.5 lectures, we'll do is, so transmission line is an actual cable. Okay, it's a, right? So we look at transmission line. This is its own physical system, right? This is not a wire. So a transmission line being high voltage and high power doesn't really look like a wire. So our goal is at the end of this 1.5 lectures, we'll say, we'll pretend the transmission line is the following thing. Okay, we'll pretend the transmission line as this. Okay, so we'll try to get to a point where we can model a transmission line in this way. Okay, that's what we're trying to get. One way is you can just pretend this is a model and not worry about how we get it. But we want to do is we want to look at slightly the basics of how do we get to this model. For example, where does this capacitance come from? Okay, why do I have a capacitor when I want to model a transmission line? Okay, so when you really model, so these two elements is standard. Okay, these two elements is sort of more standard. Right? Whenever you have a wire, we will have a resistor, and you pass sinusoid the current along the wire, it will look somewhat like an inductor. Okay, that's what always happens when you have a wire. But where does the capacitance come from? Right? Why does the transmission line model have a capacitor inside of it? Okay, and when can we ignore the capacitor and when can we not? And that requires some work to get to it. Okay, so if you read ahead or you look at this, the slides ahead, you see path integrals, you see closed form integrals. If you're a little bit worried, don't. Right, we'll get through all that. We will not use any integration. Okay, we'll use one integration, but it will be a very simple integration. Okay, well, we won't look at Maxwell equations and do the full simulation. Some people do that. Okay, you have people in companies whose job is to run full-blown Maxwell equation simulation for transmission lines. And that's not in this class. In this class, we just want to have an idea of how do we get to this sort of telegraphs model. Right? How do we get to this sort of simple lumped model? And it's good to see that at least once, right? Good to see at least once. Okay. So any questions? No more questions. We'll stop here. Right. I will update the homework. I'll update homework 6, problem 6 in homework 2. After problem 6, homework 2. Okay, so I'll do that right away. Okay, then so no questions. I'll see you on Wednesday.
Thank you, Professor.
Thanks.
Professor, I had a clarifying question.
Sure.
So back to that 3.4 problem.
Yeah.
So my understanding's correct. If we were to, so when you use 240 as the first base 1 reference, right? And then you go on and use 480 and 120, that makes sense. But so what, my question is like, what is the relationship between choosing the 240 for base 1 to having to choose what value you have to choose for base 2?
Okay, good. That's a good question. Right. So if you look at transformer 1, so we have this 0.1 per unit, right?
Right.
Coming out. So this is a per unit system. So okay, so what does this per unit involve? This involves the turns ratio for transformer 1.
Mm-hmm.
Right. So the turns ratio comes from the voltage at both sides.
And the turns ratio.
So if we don't choose 480, we need to change this 0.1 per unit. We need to change this 0.1 per unit. So that's where this comes from.
Oh, because 480 is the other. Oh, I see.
It's rated as the secondary for this transformer.
Okay.
So that's where this comes from. Right?
So for most problems, is that what we're going to be doing? Is if we have multiple transformers in a line, we'll try and make one so we don't have to change.
For most problems, we'll have multiple transformers. We'll make the secondary voltage the same as the primary voltage for the second one.
Okay. So
there's not an ambiguity of which base you choose, right? So do you go from this direction or do you go from this direction? Right? It could go from both directions. So for most problems, we'll try to remove this sort of ambiguity of which way do you look at the problem.
Right. So that's doing that for transformer 1, and then you try to adapt that to transformer 2.
Yeah, adapt that to transformer 2.
Okay, I got that. Thank you so much, Professor.
Yeah, no problem.